Alright guys, how's it going? So really quickly, I'd like to do a review of some of the things that we've talked about so far in the class for forces and give you some examples that'll help you out on the homework that you'll be doing after this video in class. So Newton's second law gave us that the net force is equal to the mass times the acceleration of an object. Basically, the power of this equation is that if you know all the forces acting on an object, and you know its mass, then you'll know how it's accelerating. If you know how it's accelerating, then you'll know what its velocity is after a certain amount of time, and then you can know where it is after a certain amount of time, and that's pretty much everything you need to know about the system. We can also rewrite this equation so that the net force is divided by the mass of the object, and it gives us the acceleration. Basically, all the problems that we do are going to rely on these facts. The next thing that we talked about on Friday was that we really want to make the distinction that mass is not the same thing as weight. Weight is another word for the force of gravity. It's how strongly we're attracted to the Earth gravitationally because of our mass, the Earth's mass, and the distance between our centers. Newton's law of gravitation, which is here, the force of gravity, is equal to some constant g times the product of the two masses divided by the radius between the two masses squared. So again, if you have two masses, the radius is the distance between their centers. So it's defined a little bit strangely. If we're talking about our weight on Earth, then we could take the gravitational constant, the mass of the Earth, and the radius, the distance between the center of the Earth and the object, we could combine those all into one term, and if we were to calculate it using each of these numbers that are given in the front cover of your book, you'd find that it's equal to 9.8, which is the approximation that we've been using so far. The mass left over is the mass of the object you're talking about, and so you have mass times the acceleration due to gravity is equal to weight. Which is something that we've been doing for a while now. Let's look at one of the examples in your book very quickly. You have the Hubble telescope example, which is example 6 on page 97 in your book. If we look at that, basically they tell us a couple things. They tell us that the mass of the Hubble telescope is 11,600 kilograms. We need to know the mass of the Earth, and so I've grabbed that from the front cover of your book, and it's 5.98 times 10 to the 24th kilograms. Again, that's in the front cover of your book, as is the gravitational constant g here. The radius of the Earth is also given in the front of your book, and it's 6.38 times 10 to the 6 meters. And then in the problem, they tell us that the object is orbiting a distance of 5.98 times 10 to the third meters, or 598 kilometers above the surface of the Earth. So this is all the information that they give you in the problem, or that is provided in the front cover of your book. The problem asks you to find the difference in the weight of the satellite between being on the surface of the Earth and being up in orbit. The common misconception is that once something's in orbit, that it stops having any force of gravity or having any weight, which isn't true. We talked about on Friday Newton's thought experiment about satellites, where if you were to launch something from the surface of the Earth and it followed a trajectory and it came back down towards the ground, if you were to fire it just a little bit faster, it would go a little bit farther and hit the ground again. But at some point, you could fire that projectile so that it was falling towards the Earth at the same rate that the Earth was curving away from the object. Essentially, that's what it is to be in orbit. You still have the force of gravity, and in fact, the force of gravity is the thing that's getting you to orbit the planet. So we expect that the weight of the satellite in space should be less, but definitely not 0. If we plug in the values for A, for the object while it's on the surface of the Earth, we'll plug in the constant g, the mass of the Earth, the mass of the satellite, and the radius of the Earth squared. We can use the radius of the Earth because the object is resting on the surface of the Earth in part A. And we'll get that the weight of the object, or the force of gravity, is 1.14 times 10 to the 5th newtons. If we redo the calculation, but this time account for the satellite being in orbit, we have, again, the constant g, the mass of the Earth, the mass of the satellite, but now the distance between their centers is the radius of the Earth plus the distance the satellite is above the surface of the Earth, which I have as r sub 0 for orbit. Add those two together, square them, type it into your calculator, and you'll get that the weight is definitely diminished. It's 0.95 times 10 to the 5th newtons, but it's not 0. Okay, so that was example 6 on page 97, and that's all we know for the force of gravity at this point. Another thing that we talked about was the normal force. Let's take an object that's resting on a table. If we draw a free body diagram, we know that the forces acting on this object are the force of gravity, the gravitational attraction between the object and the Earth due to their masses, which is the force of gravity, and then the other force is the normal force, which comes from the support of the table. And it's called a normal force because in physics, normal means perpendicular to a surface. So for a flat table, that normal force would be exactly upwards. If the object's just resting on the table, then its velocity is 0 and its acceleration is 0. But Newton said that the net force of an object is equal to mass times acceleration. If the acceleration of this object is 0, then the net force is 0. And we know what the net force is. It's the sum of the forces acting on the object, which is the force of gravity and the normal force. Since the normal force is acting upward, I have it positive, and the force of gravity is acting downward, so I have it negative. And again, we said that that has to equal 0 because the acceleration of the object is 0. If I were to solve this, I would get that the normal force has the same magnitude as the force of gravity. So this is a very straightforward calculation, but some practice with free body diagrams that'll help you with a problem that we'll be doing later this week. The last thing that I want to talk about is friction. There's two types of friction. There's static friction and kinetic friction. Static friction is used when the object's not sliding, and kinetic friction is used when the objects are sliding over each other. The force of friction is either going to be F sub s for static friction or F sub k for kinetic friction. Both equations are very similar to each other. They have a mu, which is the coefficient of friction, and it's given to you experimentally either through a table or some mode of information in your book or on the internet. The coefficient of friction is unique between any two materials rubbing on each other, and it also depends on the geometry of those surfaces, how rough or smooth they are. Although it can be a little counterintuitive where two very, very smooth surfaces can have a very large coefficient of friction. The coefficient of static friction is determined when the objects are not moving, and the coefficient of kinetic friction is determined when the objects are moving. The other part of the equation is the normal force. So the higher the force of gravity, the higher the normal force, and the higher the normal force, the bigger the friction. So if you were to press an object down onto a table, you'd get a higher normal force, and you'd get more friction out of it. The inequality that you see here in the static friction equation is due to the fact that if I have an object that's not sliding, sitting on a table, and I apply a force to that object, the static frictional force will resist that object moving and keep the object stationary, as long as I don't exceed the maximum static force that's available due to the coefficient of friction and the normal force. So when you use the equation to calculate the static friction, you're really only getting the maximum static friction allowed, and you have to decide what number to use. So I can give you an example real quick. Let's say that we do have this object up here in the corner, and let's say that the coefficient of static friction is equal to 0.2, and the mass of the object is equal to 10 kilograms. We can find the force of static friction by saying that the force of gravity in this case is 9.8 times 10 kilograms, which is equal to 98 newtons. Since it's a level table, the normal force will also be equal to 98 newtons, but it'll be pointed upward. And since the coefficient of static friction is 0.2, we can find that out. So the force, the force of static friction is either less than or equal to 0.2 times 98, which is, let's see, it's about 20 newtons. So what that means is if I were to pull on the object with 5 newtons of force, the frictional force would resist it with 5 newtons. If I was to pull on it with 10 newtons of force, the frictional force would resist it with negative 10 newtons. All the way up to 20 newtons of force. If I was to push on it with 21 newtons of force, I would exceed the maximum static friction. The object would begin sliding, and I'd have to calculate a kinetic friction problem. Okay, so your guys' homework for today is on page 128. And let's see, where is it? Here's everything that we talked about today. Your homework's on page 128, and it's 38 through 42. When we meet again on Wednesday, we're going to be talking about Atwoods Machine. So if you want, you can look through this problem. Atwoods Machine is this. It's a single pulley with a mass on either side. So let's call that mass 1, and let's call that mass 2. And it has an interesting property. So if you want to diagram this, you would make a free body diagram for both objects. So you'd have the force of gravity for the first mass, and you'd have something called the force of tension here, which is the tension in the rope that's keeping the mass from falling away from the pulley. Over here, you would have the force of gravity in the second block and the force of tension in the rope. The force of tension between the two objects is the same. The force of gravity is not, so we could write two equations. We could say that the sum of all the forces is equal to the force of gravity in the first object minus the force of tension, and I've made this direction positive, and that's equal to the mass times the acceleration. And for the second block, I'd have negative the force of gravity plus the force of tension equals mass 2 times the acceleration, and you could solve that from there. And we'll talk more about the